All right, this is chapter 19. We're going to start with just a brief discussion of section 7, electrical measuring instruments. I don't want to talk about the mechanics behind them. The ones described in the textbook are almost obsolete now. But the important thing that I want you to know is that an ammeter, which of course is used to measure current, is always placed in series so that all the current flows through the meter. If we picture a circuit, let's just keep a simple circuit. Here's a battery. It's a 12-volt battery, something very normal. And here is a resistor. We'll let that resistor be a 2-ohm resistor. If we want to measure the current, then what we have to do is break the circuit someplace. So I'll use an eraser and create a little opening here. And connect our ammeter. Now, we already know that if we have a 12-volt battery and a 2-ohm resistor, that our current should be 12 volts divided by 2 ohms, which will be 6 amps. When we add our meter, we do not want our meter to change the current through the circuit. So in order for the current to not change, an ideal ammeter should have 0 ohms resistance. In other words, you don't want the meter itself to change the current in the circuit. The reality is anything you put in a circuit is going to have some resistance. So what's important is that the resistance of the ammeter just be very, very small so it doesn't affect the current. Okay. The other meter that we use is a voltmeter. Voltmeter, which is used to measure potential difference. Remember, it is a difference. One point will be at higher potential than the other point. It is always placed in parallel. So here's that battery, our 12-volt battery. Here's the resistor. We had that 2-ohm resistor. If I want to measure the potential across this resistor, I would draw it something like this. The meter is actually running side by side or in parallel with the resistor, and it will tell you that potential difference. I might point out it's going to measure 12 volts. If we assume that these wires have virtually no resistance, the potential at this side is plus 12, the potential here would be 0, we would expect to get 12 volts. Okay. An ideal voltmeter would have infinite resistance. Well, why infinite? Well, if it has low resistance, then current that would normally go through the 2 ohm resistor would in fact flow through the voltmeter instead. We don't want a large current flowing through our meter, because if we get a large flowing through our meter, then the potential difference actually will not measure well. We don't want to change the current in the circuit. So an ideal voltmeter would have infinite resistance. Okay. Again, in real life, you cannot have a voltmeter that has infinite resistance. In reality, voltmeters have a very large resistance, because they wouldn't even work if at least not some small sample of the current actually has to flow through the meter. So in reality, they have a very large resistance. So what you want to know is that ammeters are placed in series. They need to have a very small resistance so that they don't change the current substantially. Voltmeters are placed in parallel. We usually think of measuring across with a voltmeter, and their resistance should be very high so that they do not change the current in the circuit. Okay, our last topic today is going to be, whoops, that's not what I want to do. This is section 19.8, resistance, capacitance, circuits. These are normally called RC circuits. So, suppose we have a battery, and we want to use that battery to charge a capacitor. But usually when it's done, we also have a resistor. So here's our resistor, here's our capacitor. We're all set. Oh, I want to switch. Here's our switch. And right now the switch is open. So at time t equals 0, we close the switch. Okay. Initially, the capacitor is uncharged. So we start off with no charge on the capacitor. If the capacitor is uncharged, the voltage across it is 0. So what does that mean? Let's suppose that this has some value we'll call E. There's our EMF device, our voltage. Basically, it means that at the beginning, if we think about it, the voltage across the capacitor would be 0. The voltage across the resistor would have to be E. Another thing you want to think of, while this switch is open, we have no current. We use a lowercase current here because this current is going to vary with time. And we always use a lowercase I for time varying currents. If we have a steady current, we use that capital I. And initially right here, Q is also going to be 0. The switch is open, there is no current flow, the capacitor is uncharged, the resistor has no current flowing through it. So, at t equals 0, the switch is closed. Initially, the capacitor is uncharged and the voltage across it is 0. initially, and this is right after we close that switch, the voltage across the resistor is E, and the current I will equal E over R. So we close the switch and we take a measurement right immediately after t equals 0, right away. We momentarily will have a zero potential across the capacitor. We'll have a measure of E across the resistor. We know that the capacitor initially has no charge, Q is 0. But as soon as we close that switch, current starts to flow. Let me draw the pictures of what happens once we've closed it. Obviously, current's going to flow. We're going to have that I flowing this way. And we're going to start charging. We're going to get a plus Q on this plate and a minus Q on this plate. And it's going to keep charging until that capacitor is fully charged. So really, this goes with this picture. Only very, very briefly is that voltage going to be 0, because it's going to start charging immediately. Same thing with the current. The current will initially be E over R, but as the capacitor charges, that current is going to decrease. So if we think about the potential from A to B, that's IR. Whoops, let me make that lowercase. It's whatever the current is at that moment flowing through the resistor. If I think about the potential here, potential is Q over C. All we're using is using those rules. We know V equals IR for a resistor, and we know that V equals Q over C for a capacitor. Here's our EMF device. We get an equation that says that the total EMF has to equal IR plus Q over C. Now, this is something we don't know how to solve. This is a differential equation. Now, if you're taking calculus right now, some of you high school students may be taking calculus right now, it's a differential equation because the current I is equal to dQ dt. We are not going to solve this differential equation in this class. We're just going to talk about the fact that the solution is a differential equation. Eventually, the capacitor is fully charged and I is equal to 0. Remember at the beginning, just a minute ago, right when we close it, we get I was equal to E over R. But if we wait long enough, that current will fall to 0. Initially, the capacitor was completely uncharged with a charge of 0. If we wait long enough, the charge will increase to EC, to the voltage times the capacitance. So this gives us some new formulas. They're a little different than our other formulas. Like I say, they are in fact the solutions that you get to this differential equation. But here they are. They're on the formula chart. Charging of an RC circuit. The current at any moment in time is equal to I0 e to the negative t over RC. And that initial maximum current is simply E over R. That's the current at t equals 0. That maximum current. The charge on the capacitor in this is the final charge times 1 minus E to the negative t over RC. The maximum charge, or Q final, is EC. So those are some important equations that relate to the current that's flowing through an RC circuit while it's charging, and also the amount of charge on the capacitor as it's charging. If we graph those, they look like this. We have some maximum current that we'll call I0. And you'll notice it falls off exponentially, but it won't ever actually equal 0. It may get very, 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 very small. At the time t equal RC, notice if t is equal to RC, this just becomes e to the negative 1. The current would actually be at that point I0 over E. If we make a graph where we look at the charge, there is a theoretical maximum charge Q final that we would hope to eventually reach. But it starts off with a charge of 0, and it goes like this. It really looks more logarithmic in a sense. Notice there's no point where this e to the negative t over RC actually equals 0, so that this, where this whole expression will actually equal 0, but we will approach that. At that particular point, again, this is time. When t is equal to the value of RC, this will be 1. And this would equal Q final over E. So slightly different shape. This quantity RC, we use this tau symbol, is called the time constant. It may seem odd, but the units of resistance times capacitance does actually come out to be seconds. If this time constant is small, the capacitor charges quickly. Obviously, if it's large, then the capacitor charges more slowly. When the time t is equal to about 10 times the time constant, Q is equal to about 99.995% of Q final. In other words, for practical purposes at 10 time constants, you're probably fully charged, even though there may be a minuscule amount of continuous charge. You can also get equations that describe what happens when you discharge the capacitor. After you finish charging it, if you discharge an RC circuit. There's again a current that's going to flow. It actually looks just like our previous current. We'll have a fast current followed by eventually no current. At t equals 0, we have this initial current that's equal to E over R. The charge on the capacitor will be the initial charge Q0, and it will gradually die off. Again, that initial charge Q0 is EC. The maximum charge when you're charging the capacitor is EC. If you discharge a fully charged capacitor, then obviously it starts at EC and then it decreases. The graph of this, the current would look identical. If we graphed the charge now for discharging, you would start at Q0, which would actually be the same value as that Q final right there, and it would too go through and look like that. In this case, these two graphs look identical in shape. All right, let's work a couple of examples. This is number 57 out of the textbook. And it says we have a capacitor that is 6 microfarads. We have a resistor that is 1.5 times 10 to the 5th ohms. If the capacitor is fully charged, and I'm not reading all the words in the problem, obviously, what percent of charge remains after 1.8 seconds? All right. This is a discharge problem. We're starting with a fully charged capacitor. We're asking about charge. So our formula is Q equal Q0 e to the negative t over RC. It's helpful to go ahead and get the time constant, and we can know what that value for RC is. The time constant RC is going to be 1.5 times 10 to the 5th times 6.0 times 10 to the negative 6, which turns out to just be 0.9 seconds. If we multiply that by 10, that tells us that in about 9 seconds, we will be virtually fully discharged. But we're not asking about 9 seconds. We're asking about what the state will be after 1.8 seconds. If we divide Q by Q0, that will give us the ratio of the charge to the original charge. E to the negative t is 1.8. This was 0.9. And that comes out to be 0.1 0.35. That's the ratio of charge to the original charge. That is 13.5%. So after 1.8 seconds, there's approximately, well, we really only have two significant digits, so let's change that to 14% of the charge is still on the capacitor. Let's do one more problem. This one's number 61 out of your textbook. It says that we have a 1.0 microfarad capacitor that is being charged. So this is a charging problem by a 9-volt battery through a 10 mega ohm resistor. They want us to find the voltage or the potential across the capacitor at 1 second, 5 seconds, and 20 seconds. We didn't even have a formula for potential, but we're about to get one. We know that the charge across the capacitor is Q0e to the negative. Oh, we're charging. I gotta get the right formula. When we're charging, our formula looks like this. 1 minus e to the negative t over RC. But they tell us that this maximum final charge, we called it Q final, this final charge under this situation is EC. Well, what is potential? Potential is Q over C. If I divide by C here and here, this is going to give me the potential at any given time is equal to the potential times 1 minus e to the negative. There we go. We could have had this as a formula for potential, and there's really no reason not to. It's an easily acquired formula. This is when we're charging. Remember, when we're charging at t equals 0, this would be 1. There would be absolutely no potential. If we're discharging, we would take the other formula and we would end up getting that our potential is E times e to the negative t over RC. But I got it the same way. We're not using the discharging right now, but I want you to see that it's really easy to get these formulas for potential. All right, so let's go back and see. What's our time constant? Just saves us work if we know what RC is. Our time constant in this case is 10 mega ohms, which is 10 times 10 to the 6th, times 1 microfarad, which is 10 times 10 to the negative 6 farad. That's just 10. Our time constant is just 10 seconds. So if we want to find the potential at these various times, we just have to put in our initial voltage. Our EMF is 9 volts. 1 minus E. For 1 second, it's going to be 1 over 10. If we want to do that again and we want to do it for 5 seconds, that's going to be 5 over 10. And then if we want to do it again for 20 seconds, so now I just need my calculator and I can quickly get all of these values. This one comes out to be 0.86 volts. This one turns out to be 3.5 volts. This is 7.8 volts. Remember we said earlier that you probably will be fully charged or fully discharged after about 10 time constants. That would be 100 seconds. If we do V equals 9, and we go all the way to 100 seconds, let's see what that gives me. That came out to be my calculator says 9995, but you can see to 2 significant digits, this has been fully charged. Okay, that finishes up chapter 19. There's a lot of stuff in this chapter, so go back through it slowly but surely. We're going to practice lots and lots of problems in hopes that chapter 19 will be something we can feel really confident in.